Just let me
Oh, yes.
let me say that we are back. That we are back after coffee break or tea break or whatever. I'm still dealing with admitting people. Now we'll have the math tutorial given by Adam. And Adam, how to say what is the statement? The floor is yours. Yeah, the screen is yours.
Yes,
So you
thank you.
are welcome.
So, okay. Hello, everybody. Let me share the presentation with you. And I hope it will work. Okay. I believe that you should see right now the screen. And one more time, hello everybody. Today I will talk to you about mathematical tools overview in examples. And first, one thing I will reiterate what was said by Professor Krug during earlier presentation. This presentation is, how to say, very, very basics. For anyone with the more physical or mathematical background, he can easily skip this presentation because I can not iterate enough times. It is very, very basics. However, from our experience with explaining the NMR to the people, it is beneficial to sometimes remind us about these very, very basics. So we will start more on the more even floor, everyone, when we talk about more advanced things about the NMR relaxations. And second thing which I would like to say that how to say this is not this I will touch many few things during this presentation, and it's not how to say that they create one constant order. It is more like I will couple separate thing touch which are connected with each other but very, very loosely. Okay, so first things about what I want to say is one moment, because for some reason I cannot change the slide. Okay, I believe the slide has been changed. So first, we during our presentation, during our work, we very, very often we say that we fit some model to some values. So to start it, let's say what we mean by that. Okay, we have some gathered experimental results. We want to use it to describe the reality, describe what was going during our experiment. For that reason, we need model. And usually, the model have not only depends not only is some function which not only depends on the caderic experimental results. In this case, it is x-axis and y, but it also depends on many other I say the parameters, value key1, key2, key3. But but in the most basic models, it can be, for example, one parameter. And to be clear, why I say this is I have wrote here as x-axis and y. We sometimes have models which describe that for example, we use here we gather here from in our model two examples in two x-axis. So for example, it can be frequency and temperature we measure, and our model describe what we get. And we have in the fitting is procedure which allows us to find a value K1, K2, K3 based on known experimental results. And it is why it can be used done by, how to say, the pen and paper. Usually it's done by computer programs. For example, it can be Excel, Origin, MATLAB, Vitea, which you will learn more in tomorrow lectures. Or if you are, if you know something about the programming, you can write program yourselves. So, okay, this is the basics, and let's say the example to make better show you what it's about. As I can say it, and as you can see, it will be very basic, very basic lecture. So let us assume that we want to know the speed, how the car have been traveling. And we assume, and we, or to be more exact, we know that car was traveling without acceleration. And we have data. We have distance which was traveled, and we have time. And obviously, obviously, as we know from the high school, the model so-called the model in this case is that distance is speed and times time. This equation, this here is our function which will be fitting. Obviously, in this case, our experimental data S is distance, T is time. Okay, so now quick questions to you. And of course, we want to get our speed velocity from this. If maximum traveled distance was 250 meters, and it took our car time about around 50 seconds, what was the speed? I will give you 2 minutes. You can write the answer in the chat, and we then do the example of the fitting. Okay. Okay, it was obviously how the Carol it wrote 5 meters per meter per second. Okay, I will go here now to the origin. One moment when I change the shared screen. Okay, one moment. I believe that we here have we have here one we have the screen shared, and I have little problem because the Zoom manipulation was have hide me in the menu, but okay, we have here the data. And as I said, usually we are doing the fitting with the some programs, and Origin is one of more popular. To fit, we put we highlight the data which we want, and then we go here to the fitting. In this case, it is simple linear fit, which we can fit. Okay. Fit control. Okay. As you can see, the fit gives now us the answer which was given by the Carol, which is the slope, which in this case is the speed which was fitting, is around the 5 meter per seconds. And as we can see, usually when we use the programs, we get additional parameters. First of that is, of course, because the first one of that is R square. R square is the parameter of fitting, which shows us how good the fit was. So to be more, how to say, at the most basic level, it says us in how many percent the fit reproduce results. And if it is 1, it means that it reproduces results 100% accurate. And this is one of the few ways to compare whether our fit is good or not. But to be clear, it is not exactly the best value because it strongly depends on the type of the fitting which we will be doing. Because if we, how to say, if we have sometimes we will be having if we are, for example, some fitting, I don't know, more, absorbance spectrum achieved from molecular dynamics, and compare this to the absorption spectrum compared to the get from the experiment, then even if we have R square around 0.9, 0.8, it will be very good. But sometimes, for example, when we fit magnetization in our in NMR, well, then the R square it can be 0.999, and it's not good. It's actually the fit is not enough. We have to change a model. So it's why this R square is, how to say, describe how fit is good. We have to always check it with our own eyes, and to be, how to say it, we have to always try. Well, it depends of the what we are fitting. We have to look differently depending what we are fitting. And for example, these results here were very straightforward. As we can see, it fitted it perfectly. But usually, when we have we get results from experiment, each experiment have been measured with some errors. For example, I will change little this data, and for example, it can look like that. As you can see in the previous fit, it reproduces data, but it's not the data itself not aligned perfectly on this on this plot. If I would try to fit the second set of data, yep. And to be clear, these results are the speed which should. Someone wanted something to say? I'm sorry. Okay, no, I'm sorry. When we look on the results which we got, where firstly we got here that such results which are very close in the speed of the slope we got is very similar. But our intercept, while we wasn't this intercept was the point of the start of the car, it's not in this case 0, but when we in that case we always have to check when we got physical results, we not only have to look on the results, but we have to check whether on the errors. And usually the fit is good if the error, if correct value is the result of the fit in the area between, if we subtract group add 2 times error and the results fit into this range, it is considered good fit. But as you can see, this can be sometimes tricky because, well, my old mathematics teacher during my study on the university was sometimes tells that something in the math is craft. So, you know, it's just algorithm. You do this, and you got correct results. And sometimes then we have some in the mathematics act as art. You have to intuitively try to understand what to do. Fitting is one of these such procedures. Okay, so to what? Okay, and let me come back to the presentation for a few moments. Okay. Okay, one moment. I believe that you one more time see the presentation. Um, the fitting not only allows us to find the parameters which we want, but sometimes we also use it to try to distinguish which model is incorrect. For example, one more time, we measured distance and time of the car, but this time we don't know whether it is traveling with the no acceleration or with some acceleration. And okay, so one more time. If maximum the distance is 60 meters and the time is 20 seconds, what velocity we expect? As we expect velocity around 3 meters per second. I'm sorry, I got in the wrong. And as we can see here, the results here is not correct. If we would look on the R square, it actually wouldn't be very bad results. It would be around 0.97. So the results of the parameter of fit wouldn't be so bad, but we can clearly see that on the beginning here and here of the fit, the expected results from the models and experimental ones doesn't align. And if we check another model, this time in constant acceleration, where there are 2 parameters to fit, we can see that, well, the fit is much better. And frankly, that means that this is wrong and this is right. But to be clear, it's the fact that the fit is better doesn't mean always that the model is better, because usually we have to first check whether the first model was wrong, because sometimes because the fitting is mathematical procedure. The mathematical procedure doesn't know true reality. they just check the numbers. And therefore, usually, if we give the model more parameters, then the model itself it will better reproduce reality, even if actually this model doesn't make sense, or the addition to the model, to be more exact, doesn't make sense. Always more parameters to fit may give us better results. So first, if model with less parameters, like here, we fit only just only speed with it, will be enough to explain. We don't have to compare it with another model. For example, if we come back here, if I would fit if I would fit with that with the errors, with the error one and the fit, we actually would get better results with acceleration. But it doesn't mean that it's a true good model, because the model without acceleration allow us to explain these examples. Okay. Now let's change a little the subject, and sometimes during the when we'll be showing you our models, the calculation, there will be such strange sign like this. We call this integral, and just quick how to say uh, quick reminder or explaining what does sign means. In the most basic saying, this sign, which usually have to have two numbers, b, in this case b and a, says that if we go by the x-axis, this because here we have the x-axis, this sign is value of surface under a plot of fx, and of course with the value is positive, we add this surface. If value is negative, we subtract this surface. In the most basic way, this is simply the integral. Of course, the calculating this surface is a little more problematic, and if, for example, you very often use Riemann integral, so when we want to when we explain how to calculate, we divide this area between a and b on the infinitely small rectangles, and we can calculate their surface by measure this integral small and distance, and measure the value of a function here. And one more very important properties, which I am saying here because not because you will be needed this, but because it's something I think feel wrong not to speak about integral and not to say it about it. When we calculate in this fastest way, when we calculate integral analytical, so not using numerical tools, but try to analytically get type of the function, this function, if we under the integral we have derivative of function f, and then results of the this of the integral, it would be function of f in place of b minus f in place of the a. Okay. So now okay, little more problematic problem than the last one. If we, for example, we have constant function about value of 1, and we want to measure the integral of it from 0 to 5, what will be a value? So I will give you a few moments. And let's check whether someone will be able to calculate it. And yes, one more time, Carol is correct. The value here is 5. Uh, okay, 5, because well, when we go by the when we look at this from the surface problem, we have a rectangle which which y value is 1 because it is 1, and the x-axis value is 5, and the size of the side is 5. So well, obviously it is the value of this function is simply 5, and of course we can do it from this. If someone knows derivative, and to be clear, this is the most, I believe this is the most problematic mathematics which we'll be talking about here. So don't worry. If we have derivative, if it is we have constants under the integral, derivative from which we got constants is function x. So if we to get one, we have to make derivative from the x. Okay, let's go further. And as I said, the previous one was probably the most, from my point of view, it was most, how to say, problematic mathematics, most advanced. Now we are going to, I believe, the most basic things which we will be talking about here. So what is exponential? Uh, to be when we have it is we very often here we'll be talking here about exponential, especially about one which we will be talking a little further during the lecture. And what is exponential? When we say that b is power up to n, we mean that we take b and multiply it n times. So for example, we have b to up to 2. So we take b and multiply by b. If we have b up to power of 3, then we have b multiply by b and multiply by b. And of course, well, this if b is positive, then results of such multiplying, it will be also positive. Here we have a plot how this function looks for the case of the the 2 up to power of x. And when I say power, this n we call power, b we call base of exponentiation. And one more example, probably the most simple one during this entire lecture. Try to calculate this. It's very simple. As I said, it will be simple lecture. I will give you two more, let's say 1 more minute, and we move on. And yes, Carol is one more time correct. Obviously, 2 up to power of 3 is 8, because 2 multiplied by 2 multiplied by 2 is 8. When we have power negative, that means that we divide by this number. So we have 1 divided by 8, so it is 0.155. Anything to up to 0 is 1. Well, except 0. And then the last one is 5 up to 3 is 125. Okay, so this was exponential. Now, the second part, which is logarithm. And from my how to say, experience, why the exponentials is for most people is very easy to understand. For some reasons, many have problem with logarithms. So if we say that logarithm of base of a from b is c, that means that up a, czyli that base up to this c, or in other word results, give b. So in other words, logarithms describe us to what number we have to do exponentials of the base to get the b, to get the number which we are doing logarithm from. And logarithm is, as we can remember, the exponential usually goes very fast forward. Logarithm actually goes much slower. And here we have logarithm of 10, because usually what we usually as interest as here, it will be 2 types of logarithms. One logarithm of natural logarithm, of which base of which we'll be talking shortly. And second, it is usually logarithm of 10. So in other words, when logarithm of 10 so this is our 2 basic logarithms. And one more time, some short and very well, it is not exactly the most important thing to say here. It felt very wrong to speak about logarithm and not to include this equation here, because it is one of the most important one for logarithm. If we have logarithm of d multiplied by b, then the result of this logarithm is logarithm from d plus logarithm from b. It is probably the most important properties of logarithm, and frankly, one of the reasons why we use it. We use a logarithm, but to not to how to say prolong this, here are a few examples. One more time, let's check whether there is well, whether you can do it. And one more time, I will give you, let's say, 2.5 minutes, or maybe shorter if someone will be able to do it. Yes, first one is free, is correct. So the two people write on the first one free, and it is correct. For the, yes, two people also write for the second one, and it's also correct. And the third example is also free because 10 up to 3 then gives us 1000. If we logarithm of any base from 1 is 0. And the last one, well, and I will say it wrongly. Ilaria have wrote minus, that the last one is -2, and right, it is obviously -2. So okay, so why we want to use logarithm? Well, firstly and foremostly, because we very often will use logarithm scale. To put it simple, when we make the plot, instead of, and we use logarithm or logarithm scale, then instead of value of x, we put as it was logarithm of base of 10 of this value on the plots. Or to be more exact, program do this for us because usually nearly all programs has ability to change between one type of scale and another. Well, obviously, origin has that, and for this is, for example, plot where we have uh, well, on we have here plot of the function x is equal to x because well, both of the sides are equal. And here we have, for example, how it change when we change y-axis to the logarithm scale. It, well, as you can see, we have similar plot to logarithm, to simple logarithm. Oh, and here we have, when we change the x scale, how it will change our plot, then the same result which here were simple equal line, here change to exponential function. If you, of course, you make both the logarithm on the both the x and y axis, then the results will be one more time for the one more line, straight line. Why we do this? Because if we use this because we very often have data experimental or calculated ones, which goes through many orders of magnitude, magnitudes. So, for example, if we look here on this correlation of functions, this is are from the current on the from the article which we are currently working. As you can see, I tried to fit here uh, exponential function, and as you can see, the fit on the first glance looks quite good. It's not perfect because, as you can see, it's little it's not aligned in the perfect tree, but it's not look bad. But if we use the logarithm scale, we clearly see that while in this area of the big numbers, the fit is not the worst, here in the area of the smaller number or smaller numbers, the peak differentiate very substantially from our results. Our model, which we use it to fit, is not correct. This is another example. This is one from the article which published in the previous year. Here are the relaxation function of the protein bovine serum albumin in the water. If I would use logarit scale of the logarit scale on the both x-axis and y-axis, then as you can see, this plot is totally not readable. We cannot see anything what goes here. So of course, because the first results are such big that these results, well, we cannot see what is going on. If we put the results on the logarit scale on the y-axis, it becomes much more readable. We can see what happens here. We can see that here we have some very different results and so on. And the last one is when we put both of the x-axis and y-axis on the logarit scale. Now we can clearly see what's going on. And frankly, this is the reason when we very often use logarit scale. Because without it, we cannot see clearly. Of course, we can try to when we were in normal scale, we could try to enlarge this area, check only this area, and then only this area. Of course, we could do this, and using enough times enlarging and enough time plots to showing an article, we could also show this, but using logarit scale is simple. Okay, now we move further. So there is a number which is wrote as E in mathematics and physics, and this number, well, it's not your it's a real number, but it is not very long, and it is goes much harder. It doesn't end anywhere. And this number is called by many names. Euler number, oh, actually it should be number. It is sometimes called space of natural logarit, and so on. We calculate it, and frankly, this number, how to say it, when you go to the high school, elementary school, you learn what is the p number which you use to calculate field of the circle. And frankly, from the physical and mathematical point of view, this number here is equal importance as the p number. However, it sometimes not always appears in the high schools. Of course, it depends on the country, but in the Poland, very often it's not appearing in the during the high school. And frankly, the E number is results of such equation. Here, if we go to n, which is goes to infinity, so we trying to when we write something like that, we are writing that we are limiting n is going to as close as infinite as possible. So it still goes to up, and we check whether this have some limits, whether this have any possible how to say, we can say that it goes up to some numbers, and in this case of these equations, it goes to this number. This is another one of its another of these properties, that is, if we divide E is 1 plus 1 divided by 1 plus 1 divided by 1 multiplied by 2 plus 1 divided by 1 and multiplied by divided by, I'm sorry, 1 multiplied by 2 minus the 3, so 6, and so on. And now, if we, for example, someone would like to calculate it, he can see it that it's slowly going towards this value, this limit. Okay, so when we have this e number, so our question is why in this case we provide it. It is the most important thing is well, as a logarithm, natural logarithm or exponential functions. Exponential functions very often wrote in the Excel, in the MATLAB, in the many programs as simply exp from axis is exponent function where we multiplied x times. So if, for example, it would be e up to number 2, that means that it would be e multiplied by e, and so on. It is quite interesting because these previous results show us that if we put this here as e up to power of x, we can also write this as such equation developed by Taylor, or when we calculate it from this limit from the limits, it goes here. Here is how this equation looks on the plot. To be more exact, when we put both here and both here the linear scale, and here is how it looks when we put it on the logarithm scale of x axis. And the most important thing why we're using this exponential function is that the derivative from x, I'm sorry, e up to x is also e up to x. Therefore, when we do integral, it is very easy. It's actually because of these properties, it is probably one of the most important function in existence. I trying from the, of course, mathematical point of view, from the point of view of mathematics. As to be clear, you don't have to know this to understand NMR, but how to say, it also feel wrong not to include this in this presentation. Okay, so why we in the NMR usually need exponential function? Well, usually we are interested not exactly we are usually interested in such such function where we have a multiplied by e up to minus t r, where t is usually bigger than 0. Of course, as we say during the exponent the slides, when we have here minus, that means actually that we divide by e up to power t and r. And here it is how such function looks. For example, here we have x minus x, and if we would multiply it by if we would take r as 2, it goes like that, little closer to the axis. And then if we multiply by 3, it goes little closer to axis. They reach this area very close to 0 much faster. But to be clear, it never actually reached the 0. We can come incredibly close to 0 as as much as we want to close to be zero, but we will never achieve the zero. It will always be some number, just usually very small, very small. So now the question is for you, because t obviously is the time in this case, because usually when we in the physics write t, small t, then it's either temperature or time. In this case, it's time. So if t is time, what is unit of air? As usually, I will give you 1-2 minutes. Okay, but t is not the unit. What is unit of t? Or to be more exact, what is unit of the time? Of course, in the typical SI unit time of scheme. Yes, it is. The unit of that t is seconds. So as Carol wrote little further, but I of course started commenting it without him ending what we wanted to write. It is the unit of air is 1 over the second, or rather, or sometimes as we write seconds up to power -1. Okay, so why we are such interesting in such an exponential function? Because very often you have to, when we calculate when we have this magnetization, which Professor Krug talked earlier, and when we stop working and stop and it's start and disalign yourselves, we can measure this magnetization, how it changes. And this change as magnetic, as well, more or less as such function like this. And one more time, I will go here. This is actually from the same article from with the bovine serum albumin protein, such example of magnetization. I believe it is magnetization for frequency of H1 frequency of, I believe, 3.74 megahertz. So give me one moment, I will go to the origin one more time. Okay, one moment. For some reason, okay, origin doesn't exactly have some problems, but okay, I will try to this to share it. Okay, I believe that you can see it. And okay, we have here some data, the measured magnetization, and we tried. Okay, one more time. I have to change little because I cannot see the menu. And we want to try to fit in the exponential here. Okay, so we go in the origin goes here, we go here, and origin has many pre-built, pre-written the function. In this case, usually goes to I usually goes in this case to exp the one called xdk1. And if we can look to the code, it's actually very similar to what I was saying, but instead multiply by r, we divide by t1. From the mathematic, it's very similar. Just r is equal to 1 divided by t1, and we have also here constant y0. Okay, so I am ordering him to fit, and as we can see, this result is very good because it go here correctly, and if you would come here to see from the closer, it also not perfectly but aligned with itself very good. So it's and we all have to always check magnetization, which whether it is whether it is whether we can fit properly one exponent. But it is not always as the case. Let me change the one more time to the presentation. So actually, I should probably then share the screen because it will be okay. One more time. Okay. Here we have another magnetization, this time for mixture of sugar water. It is from the article which we are currently working on. And here we have results. Let's try to fit if, well, they also looks little as look as on our first look, how to say, not armed with anything mathematical. It also look as exponent. They have similar shape. But if we tried to fit it, and now one more time because we try to enlarge it. Okay, we try to fit it. Let's say one open dialog. And let's say in the fit. Okay, the R square is around 0.99754. So according to mathematics, the results explained the model explained the 99.7% of these our experimental results. But if we look closer here and here, we can clearly see that here this fits goes under the curve and go little here over the curve. If we try to enlarge here this part, we can also clearly see that, well, here are under curve and here are under over the curve. So the fit actually is clearly little different shape. This is caused because in this case it is not one single exponential, but so-called b-exponential function. So instead of the this like that, the function is described by such function, big exponential function, where we have two amplitudes, A1 and 2, and two relaxation rates, so R1, R2. As we can see here, here because I already done earlier that fit, this and black, and the Single exponential fit is done by such dashed red line. Black solid one line is B exponential. And as you can see, it's aligned with the experimental results very good. And what's more important, when we divide because when we have B exponential fit, usually we can check how look first component and how looks second component. In this case, if we do divide it into two components, then second component goes here and goes very actually I wrote in the wrong order. In the first component here actually no, good. I'm sorry, I didn't make mistake. First component have much smaller much bigger relaxation rate. So it goes up to 0 much faster. From this point around here, it doesn't give us into any how to say important part into explaining the experimental values, but it is required to explain in this part here, because as we can see, the second component aligned itself perfectly in the second with the results into this area. But we need the first component in this from the smaller times to explain results. For that reason, we have to use this B exponential function, which is simple to sum of two exponents. Okay, to be honest, I finished it a little earlier than I expected. So now, as you can see, it was very basic, and thank you for your attentions.
Thank you very much. So what would you like us to do now?
I assume
This
that
is the question to the audience. Because we still have time. Because I have some ideas what we could do, but first I would like to hear it from you. Because we have like also session 1 summary and questions. So somehow we have time like maybe 40 minutes. Adam, could you show the slide before this one? I mean, this with the exponentiality. Yeah.
This one?
Mm-hmm. Yeah, because here you split the exponential.
Yes.
The exponential, non-exponential function into two components. I just think that it would be great if you could do the same thing, but for curve which grows up.
So such curve like that.
Yes, because this will also happen.
Okay, then give me a moment. I will look for some.
I mean, I don't know whether this is of interest for the audience because we do not have feedback, but maybe such things are usually difficult. So maybe it would make sense.
Then let me just look for some results with that.
Mm-hmm.
1 moment. I believe here I will be having some.
Because p exponentiality is typically a kind of really tricky thing.
Okay, so here,
Because which function you are supposed to fit, yeah? Because here is a kind of trick, and then it's this independent parameter here.
I will try to change that only relevant data are on the here. So for example, here we have well different magnetization which goes a little differently.
I suppose it would be worth to mention that we did that in logarithmic scale. So therefore we have so many points here.
Yes. Okay.
Maybe you could also, but this is idea, I'm not interfering anymore. To show what happens if you change the x-axis to linear, because then one can see better deviations from exponentiality.
You mean change this x-axis, yes?
Well, what we should have, no, we should, I suppose, change y-axis.
So
Because
so I will go actually to this one to show it.
To just show that there are deviations from exponentiality.
Yes.
Because after all, if you have single exponential function and you take logarithm of both sides, yeah, you should get linear dependence.
Scale. And let's say to the okay, I need to go to too far.
You can change it.
Yes, I will change it. Let's say to the 5. And
People knows, oh, yeah. So one can see that just in the low field range, short time range, sorry. The obvious deviations from linear dependence.
because the deviation is here. Yes, as we can see, it's clearly
Function, you should get straight line, yeah, here in
yes,
this presentation. But here now you do not have it, and it clearly shows that this is the exponential.
yes.
Non-exponential.
Okay, so going.
Let us try another example.
So come back to, sorry, to this example, right?
Yes, if you could.
Okay, so here we have we can try to fit one more time the one exponent. Function x1 decay. Yep. And we got such a results like this. And obviously, because this is different magnetization type, I'm sorry. The here amplitude is negative. If we look whether it's, I'm sorry?
It does not matter, it's how
Yes.
the function is constant.
Yes.
Always look for the arbitrary value.
Yes, I will change here a little so we can see it better like that. We can see that in this region and this region, the results are not exactly perfectly aligning with our model with one exponential. If we try to look here, we can also see that this and this, well, the shape is little different. similarly, how to when we were doing the previous example, the shape is little have little different, let's say, bend, little different curve than given us by one exponential now. We can try one more time, use p exponential, and well, to be more exact, program will do it for us. And firstly, when we look on these results, we can see that here these results align perfectly with our experimental results. I'm sorry. If we go one more time here, it also shows that results are much. Well, actually, let me move this table here. Are much more in align to the our model to be exponential, be exponential, aligned perfectly with, well, maybe not perfectly, but very, very good with experimental results. Also, if we, for example, look for the parameters of the fits, we have here R square 0.997. Here we have 0.99994. So frankly, it's as close to 1 as we can reasonably expect. Of course, if we look for on the results of the shows, we have here this A1. I'm sorry, the T1. So the invert of the relaxation rate here is 0.26. Here is, and this is in the somehow in the middle of this 0.38 and 0.67. Because these results try to approximate the different results from here, and therefore these results from here is actually, well, let's say it, trying to emulate 2 times. So obviously it tries to be exponential, so it tries to fit to on the whole area to these results. I don't know whether there is another questions about this process. If there is any question, of course, I will try to answer it and show you how it's done.
I would have a comment, if I may, because we already encountered it many times. You know, here Adam applied a function. And in the function, you have parameters, A1, T1, or R1, A2, T1, or T2, or something like that. So let's say you have parameters which are labeled with the number 1, and parameters which are labeled with the number 2. Yeah? And quite often, we are facing such a problem. When the relaxation processes be exponential, then sometimes we have always faster and slower process. Yeah, otherwise it wouldn't be exponential. However, sometimes the variables with index 1 describe the slower process. Sometimes the variables with index 2 describe the slower process, because the software is not able to read the mind. So it's like A plus B is equal B plus A, yeah? So you have really the chance 50-50 that if you fit a data, the set of variables with the number 1 will be for slow relaxation, and with number 2 for fast, or another way around. And it can change between magnetic fields, temperatures, and so on. Each curve, if you start fitting like that, can give you both answers. It's just a really stochastic process. But one has to look. I mean, one possibility is to write a software, which, for instance, Kahinga, who is in the audience, did. However, before you write software, or you decide not to write the software, but just do it manually, whatever, you have to understand the subject. Because there are those two amplitudes, A1 and A2. And sometimes there's a question. What is the relative contribution of the fast relaxation process? Or what is the relative contribution of the slow relaxation process? Because the values themselves, A1 and A2, are never important. They just, A1 plus A2 plus Y0 just adds to 1, yeah? This is just normalization. But what is important is the ratio between A1 and A2, or A2 and A1. So A1 over A2, or A2 over O. Yeah. However, the thing is that you will never get the question, please give a ratio between A1 and A2. Because this is nonsense. What you might consider is the ratio between the contribution of the fast process and the contribution of the slow process. So you never write in a paper A1 over A2. You write, for instance, A slow over A fast. And then for each case, you must look which of those amplitude is associated with which relaxation process. And if I have expression like here, when it is divided by t, so I have t, so it means longer t means slower process. So if I look here at those t, it somehow means that T2 is longer. So the process which is labeled with index 2 is slower. So if somebody asks me what is the contribution of the slow process, I should make A2 over A1, because A2 means A slow in this case. However, then we can come to next temperature, next magnetic field, whatever, and you do the same fitting. However, the labeling is inverted. And one has to pay attention. Because summarizing this, sometimes A1 is slow, sometimes A1 is fast. So this was a kind of comment. Other questions, more comments? As I do not hear, I think we'll thank you, Adam, and maybe we need somewhat longer time for lunch. So you are supposed to meet at 2 p.m. Yeah? So more or less in 1.5 hours for next lecture. So enjoy the break.